And you let me know and we'll start.
We're good.
Okay. Aaron's good. All right. Appreciate everybody spending your Thursday afternoon with us for an hour. My name is Michael Young, and I am the now co-principal investigator of the Regional Induced Seismicity Collaborative, known as RISC. This collaborative is a consortium of state geological surveys in the southern mid-continent of the U.S. that includes Texas, New Mexico, Oklahoma, Kansas, and Arkansas. We have been really focusing on trying to look at sort of regional understanding of seismicity, the role of injection, natural seismicity, and these issues really at the state level where the data that we're collecting, it goes into the decision making by regulators, by companies, and by people. So part of that has been running a webinar series that we've been doing now for about 3 years, and we have tried to find great speakers that talk about a variety of different topics. And so before I introduce our speaker, Lisa Block, I just want to mention our sponsors. We're really grateful for support from the Groundwater Protection Council in Oklahoma and for the U.S. Department of Energy, the National Energy Technology Laboratory in Pittsburgh, which has been funding GWPC and us, and also the DOE Office of Fossil Energy. And I also want to mention that Lily Horn, a colleague of mine here at the Bureau, is now co-PI of RISC, and so you may be hearing from Lily as well in the future. So now, without further ado, let me introduce Lisa Block, who is with the U.S. Bureau of Reclamation. Her office is in the Denver Federal Center in Lakewood, Colorado. Lisa has an undergrad degree in geology and geophysics from A&M, that other excellent school here in Texas. She then got her PhD in geophysics from MIT and worked briefly in the oil and gas industry before starting government service with Reclamation in '92. She has worked on a wide range of studies, including shallow engineering geophysical surveys, seismic hazard analyses, and induced seismicity. And she has been involved with seismic monitoring program in Reclamation's Paradox Valley unit in Western Colorado for the last 26 years. So this is a little bit far afield from a typical Southern Mid-Continent application, but we're really excited to hear about this project and to see how the feds have addressed this issue of seismicity with one of their big projects. Lisa, thank you so much for being here, and I will mute and let you take it away. Thank you.
Okay, thank you for the introduction, and thank you for inviting me to speak today. Have prepared quite a bit of material, so I'm going to try to get through it and move at a fairly good pace, I think. So just a basic outline of my talk. I'd like to give you some of the project background and history of the Paradox Valley unit, and then talk about some of the historical induced seismicity patterns that we've seen over the decades, really. And then for the second half of the talk, I'd like to focus on the induced seismicity and the injection operations and some of the technical analyses that we've done in about the last 5 to 7 years. So the Paradox Valley unit, it's a component of the Colorado River Basin Salinity Control Program. That program was authorized by Congress in 1974. And the goal of that program is to reduce salinity levels in the Colorado River system, which, as probably everybody knows, is of increasing importance as the levels of water in that system go down. The project, the Paradox Valley Unit project, is jointly funded by both the Bureau of Reclamation and the Colorado River Basin Salinity Control Forum, which is composed of representatives from the 7 river basin states that use water from the Colorado River system. And the program is operated by the Bureau of Reclamation, Upper Colorado region, which is headquartered in Salt Lake City. So Paradox Valley is in western Colorado, very close to the Utah border. The valley is a northwest trending valley that was formed by the collapse of a salt anticline. it's underlain by up to 16,000 feet of salt. And because of this thick salt layer, naturally occurring brine within the valley has a salinity concentration almost 8 times that of the ocean. Under normal natural circumstances, the Dolores River, which crosses the valley right in the middle, it would pick up a large salt load from that brine, but the Paradox Valley unit was designed to intercept that brine and prevent it from flowing into the Dolores River and degrading the water quality in the Colorado River system. So here's a view of Paradox Valley looking towards the northwest with the La Salle Mountains in the background over in Utah. The brine is intercepted by a series of shallow extraction wells along the Dolores River right in the valley. It's then piped over to the single deep injection well, and that brine is injected at a depth of around 14,000 feet. The lower picture here is a simplified geologic cross-section perpendicular to the valley. So this blue is the thick salt dome underlying the valley. This is the well over here, the red line, and the Leadville Carbonate Formation is this thin yellow line. That is the primary target injection formation for this well. And this Paradox salt acts as a confining layer for that injected fluid. And the Paradox, the Leadville Formation is offset by a series of northwest trending faults, and this has affected the distribution of seismicity and how it spread away from the well. So we'll see some maps shortly showing how that has affected the geographical distribution of the seismicity. This is a simple timeline of the project. So again, it was authorized by Congress back in 1974. The Paradox Valley Seismic Network, the first stations went in 1983, and the entire seismic network has been continuously operational since 1985. So this seismic network was installed several years before injection even started. The injection well itself was completed in 1987 because they had to complete other infrastructure associated with the project. The injection actually didn't start in that well until 1991. And between 91 and 95, there were a series of injection tests conducted. Long-term brine disposal began in mid-1996. It continued up until March 2019, and brine disposal was suspended at that time pending some further studies of the seismic hazard. We had a magnitude 4.5 earthquake in March of that year. All these red circles are times when injection operations were altered in some way to try to mitigate the induced seismicity, and I'll talk to you a little bit more about those shortly. So the monitoring program, as I said, it was initiated voluntarily by Reclamation several years prior to the start of injection, so it was not originally a regulatory requirement. And the seismic network itself is an integral component of the PVU project. So it's funded from the project's operations and maintenance budget. It's not some separate research program, as people sometimes assume. And the maintenance and operation of the seismic network and analyses of the data are performed by Reclamation's Technical Service Center in Denver under a service agreement with the UC region. So that's how I enter into the picture. Myself and several other geophysicists and seismologists at the Technical Service Center basically are under contract with the UC region to maintain the network and analyze the data. So here is a map showing the configuration of the seismic network. The pink star over here next to the valley is the injection well. The original network was composed of 10 vertical component analog short period seismic stations, and those are shown by the black squares. The current network consists of 23 component digital broadband stations shown by these white triangles, as well as 3 strong motion stations shown by the green squares. So the configuration of this network has undergone changes multiple times since the 1980s. And these are just a few pictures of our equipment out of the seismic stations. The seismometers are buried in shallow vaults a few feet under the ground. The cables run to these towers. The data is all relayed in real time continuously by radio telemetry to a central data acquisition hub. It's located at a local airport there in Nucla, Colorado. And some initial processing of the data is done automatically there, and then it is sent on to Denver for further analysis. So these seismic stations are spread out throughout the area in some very remote locations. It takes, a couple hours to get to these sites down some very rugged four-wheel drive roads. And so we have a team of people that go out there 2 or 3 times a year to maintain all these sites. I just want to talk briefly about the regulatory requirements for the well, because I know there may be some people interested in that. The well is permitted by the EPA as a Class 5 disposal well. As I said, the seismic monitoring program initially started as a voluntary program, but since the network was already in place when we applied for our first permit for injection, and since we actually did record some induced seismicity during those earliest injection tests, a requirement to continue the seismic monitoring program was incorporated into the first permit that was issued for long-term brine disposal back in the 1990s, and it's been a requirement ever since. The early permit sort of included some general requirements for monitoring and reporting seismicity, but nothing really specific. But over the years, additional specific requirements have been incorporated over time. Some of those requirements include meeting minimum operating standards for the network. So those are defined in the seismic monitoring plan, which is attached to the permit as an appendix. So that's part of the permit. We have to notify EPA and inspect the injection facilities for damage following large earthquakes. And if the earthquake creates a peak horizontal ground acceleration of 0.1 G or larger at the injection facility, then we also have to shut down the well during those inspections. We are also required to perform monthly evaluations of the seismic network operating status and the recorded seismicity, which is not a big deal since we are doing that on a near daily basis anyway. And then we submit an annual report with the network operations and seismicity once a year to EPA. Some of the things that are not in the permit does not include any restrictions on the rates or magnitudes of induced earthquakes. And it does not include any requirements for having the well shut in or any other changes in operations in response to high rates or magnitudes of seismicity. So really what's in the permit is more focused on ensuring the mechanical integrity of the injection facilities rather than mitigating the impact of the induced seismicity on the surrounding communities. But having said that, the PVU does have its own emergency action plan, which imposes some additional requirements that actually go beyond what's in our injection permit. So following a large, widely felt earthquake, we actually need to do a written evaluation of the earthquake, an analysis of the potential immediate and long-term future seismicity. We also need to prepare a decision document that summarizes the findings of the seismic analyses, the facility inspections. It gives options for future injection operations and recommendations for restarting injection. So that decision document is a collaborative effort between multiple reclamation offices, and it's circulated and discussed widely and then signed officially and distributed. And really by the time all this work is done, the well would have been shut down for at least a few weeks. So here's a summary of some of the operational changes that have occurred over the years to try to mitigate the induced seismicity. The upper plot here shows the injection rate in gallons per minute, starting in 1991 and going through 2020. So this period from 91 to 95 are the injection tests, and then the continuous injection started here in mid-1996. So the first change in operations in response to the seismicity occurred in mid-1999 when we had 2 earthquakes that were in the mid-3 range on the local magnitude scale. I think they were about a month apart back in June, July 1999. And following those 2 earthquakes, reclamation started having biannual 20-day injection well shut-ins. Prior to that, the injection had really been operated almost continuously, and the well had only been shut in if maintenance was needed or if the wellhead pressures were approaching their safety limits. So starting in 99, they had 20-day biannual shut-ins, but that really didn't solve the problem because less than a year later, there was a magnitude 4.3 local magnitude or 3.8 moment magnitude earthquake. So following that earthquake, they decided that they really needed to decrease the overall flow rate. So the well was shut in for a month while they were trying to make decisions about the best way to proceed. And the decision was then made to come back online at only about 2/3 the rate that they were doing before. And that really helped a lot. Things were pretty smooth for about 13 years, not a lot of seismicity of concern. And we didn't have an increase in our maximum earthquake magnitude until January 2013, so 13 years later. And following that earthquake, we shut in for 3 months and decreased the effective flow rate by another 10%. We also changed from having the biannual 20-day shut-ins to weekly 18-hour shut-ins. And I'll show some analysis a little bit later in the talk that explains why we made that decision. And then in March 2017, we also did another more minor shut-in, about a 1-month shut-in. We decreased the effective flow rate by about 5%. And again, the weekly shut-ins changed slightly. So this change in 2013, the change in 2017, and then the suspension in 2019 is something that I'll touch on a little bit more in the second half of the talk. So this is some more of our injection data. So the top plot is those same flow rates we were just looking at. The middle plot shows the downhole pressure. This is the pressure computed at the depth of the Leadville Formation, about 14,000 feet deep. And right here, you can see the pressure dropped following that decrease in flow rate in 2000. It took several years for the pressures to rebound to what they had been prior to 2000. But then we had generally increasing pressure trend up until that 2013 earthquake. Following that 2013 earthquake, when we changed the shut-in schedule to have more frequent shut-ins, the pressures at the well themselves have remained lower than they had been previously. The maximum pressure we've had downhole is about 12,200 PSI. That occurred in January 2013, just prior to that 3-month shut-in. And the cumulative volume of fluid we've injected is about 2.5 billion gallons. For those of you who like to work in barrels or cubic meters, I'll let you do your own conversions. So here's a summary that shows how the earthquakes have evolved over time in terms of depth. So this plot starts in January 1985, which is when the seismic network became continuously operational, and it goes through 2020. And then the Y scale is just depth. And so you can see that we had a single earthquake in the 6 years prior to injection starting, and it was pretty deep. It's a little over 14 kilometers deep. But once injection started, we had seismicity almost immediately within days of the first injection test. And the seismicity occurred very close to the depth range of the perforated zone in the well. Over time, that seismicity has continued at about the same depth, and it has spread out a little bit shallower and a little bit deeper. But I really think that's more because as it spread away from the well, it's following those Leadville horizon across those faults that offset the Leadville rather than diffusing into a lot of other formations. And you can see the natural occurring seismicity tends to be quite a bit deeper. So we do have a very low rate of naturally occurring seismicity that's generally below 10 kilometers depth. So when I show you maps of the induced seismicity, I generally just show the seismicity above 10 kilometers depth because it's just a very convenient way to try to separate out the induced versus the natural seismicity. If I had to pick one plot to sort of summarize our seismicity over time, this would probably be it. This plot shows how the seismicity has evolved away from the well over time. So again, that time axis starts in 1985 when seismic monitoring began. And as I just said, I'm only going to include earthquakes that are less than or equal to 10 kilometers depth. So prior to the start of our injection in 1991, we didn't see any earthquakes less than 10 kilometers depth. Beginning with those first injection tests, we saw several right near the well. And then in 1993, there was acid stimulation done in the well. And in 94 and 95, there were some longer injection tests that lasted several months each. And so following those operational changes in 93 and 94, you can see that the seismicity started diffusing away from the well. And the envelope of that seismicity is matched pretty well by a very simple seismic triggering front from a 1D pore pressure diffusion model, the diffusivity of about 0.2 meter squared per second, which corresponds to a permeability about 5 to 8 millidarcies. So this is very consistent with the parameters from early injection testing. The couple other things to note on here is that the seismicity doesn't occur everywhere. There are some distances where we don't have any seismicity, such as 10 to 11 kilometers here. That's caused by the geologic complexity, the structure of all those faults. So you'll see when we show you some maps why there are just some certain areas where we don't get earthquakes, and it's because the faulting is directing where the earthquakes are going. The colored circles are the larger earthquakes. And so the reds are the events with magnitudes greater than or equal to 4. The pink ones are 3.5 to 4. The yellows are 3 to 3.5. And the blue ones are anything 2.5 or larger. 2.5 is about the magnitude where people start feeling things out in this area. So basically on this plot, the gray dots are earthquakes too small to be felt, and all the colored dots are things that someone could potentially feel. And so most of our felt events have occurred within 9 kilometers of the well, and almost all the larger events have occurred within about 4 kilometers of the well. Okay, so if my animation works correctly, what you are going to see here is the seismicity evolving away from the well over time. You'll also see the yellow triangles, which represent the seismic stations, pop up as the seismic network has been modified over the years. And then on the right, we will see that same injection rate, downhole pressure, and cumulative volume that I showed you earlier. So I am going to try to run this. Whoops. Here we go. You're getting 30 years worth of induced seismicity in 30 seconds. The blue dots are the earthquakes with magnitude smaller than 2.5, and those red circles are the ones 2.5 or larger. So those are the ones that are potentially felt. So you can see from this that the distribution of the seismicity around the well is very asymmetric. It tends to spread out northwest, southeast, not so much northeast, southwest. And that's because of subsurface faults that trend northwest that are blocking the flow of the pressure increase to the southwest. You also see some earthquakes lining up along the middle of the valley, and that is along one of the major structural faults in the area, but we really just think that fault's acting as a conduit for pore pressure increase. The actual slip on these earthquakes is oblique to the mapped basement faults. So it's really not the big faults that are slipping. They're just acting as either boundaries to restrict pressure flow or pressure diffusion, or conduits for pressure diffusion to go down along them. So the next animation shows that geology. So this is the top of the Leadville Formation. So the pink, or whatever color that is, peachy color is higher. The purple is deeper. All these lines are the northwest trending faults that I was talking about. The blue lines are general faults. These black lines are faults that have more vertical throw across them, and they have been interpreted as being impermeable to fluid flow and pressure diffusion through the Leadville Formation, because the throw on those faults is large enough to totally offset the Leadville Formation across them. This wide area is a place where the Leadville Formation is eroded away. The boundaries of that erosion area are not very well defined because it's really based on some limited seismic reflection data. So I'll just go ahead and run this animation again so you can see how the earthquakes evolve in relation to the geology. So they started by spreading out between these two bounding faults here. And then we actually got earthquakes pop up across on the other side of Paradox Valley. You can see them distributing along this fault and up within this fault block, this uplifted fault block to the northwest. So I think the distribution, the overall distribution of the seismicity is controlled both by the geology, and then the early onset of some of this seismicity on the other side of the valley may also be due to pre-existing stress conditions around the perimeter of that salt anticline. Because certainly the stresses around salt domes and salt anticlines can vary quite a bit. This black line over here is considered to be a fault that forms a barrier to fluid flow and pressure increase from the injection well. And you'll notice we have a lot of earthquakes on the other side of that. Almost all these earthquakes are very shallow. They're way above the Paradox salt confining layer. And most of them are small magnitude. And they've been previously interpreted as being due to stress changes just caused by the expansion of the reservoir itself. We have some of that work published in some papers. But recently, just in the last couple of years, we've gotten a few deep events over there for the first time. And some of our largest events have actually occurred over there just like less than a year ago. So towards the end of the talk, I'll show you some of those events. So just keep this picture in mind for later on. So here's a list of our largest earthquakes. We've had 7 induced earthquakes with magnitudes greater than or equal to 3.5. And 4 of these occurred in 2019 and 2020. The last 3 occurred more than a year and a half after brine disposal was suspended. So I would like to have time at the end of my talk to talk about these last group of earthquakes. So moving on basically now to the second part of the talk, really talking about our more recent operations and induced seismicity and some of our analyses. I want to start with the response to that January 2013 earthquake. I mentioned before we had a 3-month shutdown of the well, and then we decreased the flow rate from 230 to 200 gallons per minute, basically a 10% decrease in the effective flow rate. And we changed from having those 20-day shut-ins twice a year to having weekly 18-hour shut-ins. At the bottom here, you can see the wellhead pressure and just shows how we used to have those biannual shut-ins. We had the long shut-in, and then we came back at a lower flow rate, but also with weekly shut-ins. And so the pressures have remained lower at the well than they had been previously. That decision was based on some work that one of my colleagues, Vanessa King, did a number of years ago. She used some well testing software to look at a lot of different injection scenarios and try to evaluate the effect of different scenarios on the pressures, both the maximum wellhead pressure and the average wellhead pressure. The software she was using did not allow her to calculate pressures away from the well, so she used the average pressure at the well as sort of a proxy for how the pressure trends would be away from the well. So the blue dots are maximum pressures, the red dots are average pressures for some different scenarios. This is just an example of some of the scenarios she ran. This particular scenario is just a 1-year scenario with a fixed volume of fluid injection. And at the low flow rate, the injection is continuous for 1 full year. At higher flow rates, the injection is continuous at that flow rate until that given volume of fluid is reached, and then the well shut down for the remainder of the year. So you can see for the same volume of fluid injected per year, that both the maximum and the average pressures are the lowest if you inject at lower volumes with less shut-ins. So that was why the decision was made to go from those biannual 20-day shut-ins to having more frequent shut-ins, but of lower duration, shorter duration. We still need to have some shut-ins because just the need to do some maintenance on the well. So what happened after we changed that? This is some quarterly seismicity rates before and after that change in operations. So the top plot shows the quarterly seismicity rates of all the earthquakes within 5 kilometers of the well. The bottom plot shows some quarterly rates at distances of 5 to 10 kilometers from the well. And the plot starts a couple of years prior to the change in operations, which is marked by this red dashed line. So you can see that both the near well rate and the rate in this intermediate distance range from 5 to 10 kilometers, they both decrease substantially following this 3-month shut-in and that decreased flow rate. The near well rates decreased 72%, and the more distant seismicity rates decreased 81%. And that lasted for a couple of years. Unfortunately, in 2016, seismicity rates started increasing again near the well, and then at distances greater than 5 kilometers from the well, they started increasing in about mid-2016. To look at these changes in seismicity rates, we did look at some pore pressure diffusion models, and I just want to show you an example of one. What this shows is the pressure change from the day just before we had that 3-month shut-in to the day just before we started injecting again. So this is a difference in pressures. So what this shows is that the pressure change was negative here out to about 2.5 kilometers. So basically during that 3-month shut-in, pressures declined out to about 2.5 kilometers from the well. By the end of 2013, well, we started injecting on April 17th, 2013. By the end of the year, that cone of depressed pressures actually expanded out to about 3.5 kilometers for this model. But farther than that, pressures were increasing and they were higher than they were prior to that shutdown. So I'm just going to go quickly through some other time steps. June 2014, December 2014, December 2015, December 2016. So you can see that the area of lower pressure around the well is shrinking and the pressures away from the well are increasing. So we looked at a large range of models with some different parameters, and the conclusions were that basically pore pressures decreased somewhere between 4.5 and 7.5 kilometers from the well following those operational changes. But by the end of 2016, the pore pressures had largely increased at anywhere from 0.3 to 1.44 kilometers from the well, and they were up to 100 psi higher than they actually were prior to the January 2013 earthquake. So this is a good example of the Kaiser effect, where seismicity rates decrease when pressure and stress conditions are lowered, and then they rebound when you exceed your previous pore pressures. At those greater distances, 5 to 10 kilometers from the well, we may also have had some effects from stress changes due to the reservoir depressurization and then repressurization, and possibly also some stress changes just due to stress redistribution following the January earthquake itself, since it did occur in that distance range. So because of these increasing rates that we saw in 2016, and also we did see some increases in the maximum magnitudes observed during 2016, we decided to make another operational change in early 2017. This was actually the first time in the history of the project that we made an operational change in the absence of a very large, widely felt earthquake. This is one we decided to make to see if we could avert having a large, widely felt earthquake. So it was considered a sort of a preemptive operational change. And because of that classification, of course, we didn't have as big of a change. We shut the well in for 3 weeks rather than 3 months. And we had about a 5% decrease in the effective flow rate. And again, these are the seismicity rates within 5 kilometers of the well and 5 to 10 kilometers from the well. And it took a while for rates to come down. They actually remained elevated throughout the rest of 2017. And there was some discussion about having another decrease in flow rate in late 2017. But ultimately, the decision was made to wait a little bit longer and give it more chance for rates to come down. And in early 2018, they did come down, and they stayed low right up into early 2019. And then we had a magnitude 4.5, the largest earthquake we've seen. It occurred in the near well region within 5 kilometers from the well. So this plot shows you all the earthquakes within 5 kilometers of the well. And it's just a simple scatter plot of earthquakes. So the x-axis is time starting in 2018, and the y-axis is magnitude. So you can see prior to the occurrence of this earthquake, for more than a year, seismicity rates in this area were low. Magnitudes were low. I mean, we didn't have a magnitude greater than about 1.6 in the year or so before this earthquake. And then we had the 4.5 on March 4th, 2019. And we had a couple thousand aftershocks following that, a huge number of aftershocks. So here's some technical information about this earthquake. It occurred 1.6 kilometers southwest of the injection well in an area where induced seismicity has been occurring since 1998. Here's the focal mechanism, the little beach ball here. These colored circles are aftershocks, color-coded by depth. So the blue is deeper, the orange and red are shallower. So you can see this after the main aftershock cloud forms a plane that strikes northeast and dips to the southeast, which is consistent with the focal mechanism orientation of one of the focal planes. The earthquake occurred at the same depth interval as all the previous earthquakes. There was nothing unusual about it in that sense. This is just a plot of the earthquake depths over time of earthquakes within 2 kilometers of the well. So plotted right there in the zone where you would expect to have it. This is a plot showing some of the pressure trends at the location of this earthquake prior to its occurrence. So the top plot is the pressure increase relative to the pre-injection hydrostatic levels. So this gray area shows the 3-month shutdown back in 2013. You can see there the pressure was about 3,600 PSI above the pre-injection levels. It came down, it gradually increased, it exceeded its prior level late 2015 to 2016, which is when we saw seismicity rates and magnitude start to increase. We had that other shorter shut-in in 2017, pressures decreased again and then gradually increased. And at the time that this earthquake occurred, they had just about reached or slightly exceeded the maximum pressure from 2017. This middle plot shows the temporal pressure gradient. So positive bars pointing up means pressures were increasing at that location. Negative bars means the pressures were decreasing. You can see that prior to 2013, when we were having those biannual 20-day shut-ins, at this location's pressures were actually decreasing twice a year. Once we stopped having those longer shut-ins and we went to the shorter weekly shut-ins, pressures were generally increasing continuously, except for following the short shut-in in 2017. So at the time of this earthquake, pressures were at their peak level. They had been gradually increasing for about 6 years. And the spatial pressure gradients were also relatively low. In fact, all the changes we've made to try to mitigate the seismicity from having more shut-ins to decreasing the flow rate have basically caused the spatial pressure gradients to decrease over time. So at the time of this earthquake, we had pressures that were high in terms of absolute values. They had been gradually increasing, almost interrupted for 6 years, and the spatial gradients were low. So these are some things that we could consider whether or not these are favorable conditions for the occurrence of larger magnitude earthquakes. Here's some cross sections through this main aftershock cluster. It's some pretty interesting distributions. This red dot here is the hypocenter of the main shock. The black dots are aftershocks within this main aftershock cloud. So this cross section is parallel to the fault plane, and the cross section on the right is perpendicular to the fault plane. So what I want you to take away from this plot is basically that we have some very distinct layering in these aftershocks, and that suggests to us that these aftershocks are being largely controlled by the geologic layering, and it suggests that we have 2 brittle layers and a more elastic or plastic layer, I should say, in between that's more resistant to shear failure. We wanted to further investigate that, so we tried to look at how that aligns with our injection formations. And the existing geologic models are not real consistent with the aftershock geometry. These are 2 different models of the top of the Leadville from 2 different investigations. And you can see the top of the Leadville shown by the red dashed line and the blue dotted line overlaid with our aftershocks. And one has, faults going right through the aftershock cloud, which we clearly don't see in the aftershock distribution. And the other one has the entire aftershock distribution being above our injection layer. So we decided to try to investigate this a little bit farther. So what we did was we actually did a hypocenter velocity inversion, but this is a relative hypocenter velocity inversion where we used time differences from waveform cross correlation, so they were very precise. And we just inverted for the P wave velocity and the relative event locations with a center of mass constraint. So we used data from about 1,200 earthquakes that were recorded from 1991 through 2019. Those are the green dots on this map. The pink line here is a cross section through the final velocity model. I should say this blue rectangle is the area within which velocities vary during this inversion. All the velocities outside that rectangle remained fixed during the inversion. So we got this velocity model that showed a pretty layered velocity model with a low P wave velocity layer underlain by an anomalously high P wave velocity layer. We then correlated these velocity structures with the well log in the well. So where these orange circles are, we extracted vertical velocity profiles. Those are the colored lines plotted on the right. And we compared these vertical profiles with the well log, which is this dashed gray dashed line. So you can see from the sonic log that there's a sharp velocity contrast right at the top of the Leadville. The Leadville is the highest velocity layer in this depth range. And these paradox salt members are some of the lowest velocities. And so we just shifted our velocity model vertically until we got a reasonable match. We had to shift up about 500 meters to get a reasonable match to the well log. And then we just overlaid those boundaries on the aftershock distribution, and it indicate that indeed the main hypocenter and this deeper dense aftershock layer correspond to our main injection formation, the Leadville formation. And this aseismic zone corresponds more or less to the paradox salt members, the confining layer. There, we did just draw this in as a purely horizontal layer, but I'm sure there's some undulation in that salt, the top of the salt, because it's a very plastic formation that flows easily. And we interpret that there was some of our models, as you recall, were showing that there was a fault going through our aftershock cloud. We believe that fault is mislocated and probably should be farther to the west. So the fault plane may have ruptured up until it hit that boundary fault. Some interesting things that comes out of this is that you can notice the aftershocks within the Leadville and deeper are the largest ones. And these aftershocks that are occurring just at or above the confining layer tend to be much smaller in magnitude. We went and looked at the Gutenberg Richter distribution. You can see a distinct difference in the B values. So the deep aftershocks have a B value of about 0.62, meaning that they have a larger fraction of larger magnitude earthquakes, and those shallower aftershocks that are above the confining layer have a B value of about 0.9. I did just recently look at let me go back one. This data was done with the early data from March to July 2019. So I did just go back and then do this again using the later data. So starting in August 2019 and going to just last month. And you can see that over time, the B values are becoming more similar, 0.67 and 0.77, and the Gutenberg Richter distributions are becoming more similar. So I'm not sure exactly what that means right now, but it does suggest that maybe the stress conditions above and below the confining layer are becoming more similar over time. We also saw distinct differences in the aftershock decay relations above and below the confining layer. The deeper aftershocks had more aftershocks, but they fell off at a faster rate than the shallower aftershocks. So very distinct differences in those trends. And again, we updated those relations recently. And what this plot shows is the blue line is the data that was used to do those initial Amori aftershock fits. The red line is just projecting those fits out to the future. And the gray line is what we have observed. So this top plot is for a magnitude threshold of 0. The bottom plot's for a magnitude threshold of 0.5. These plots on the left are for the shallow aftershocks above the confining layer. So they show that our observed aftershocks are matching up with the predicted equation pretty well. But the deep aftershocks, however, are falling off at a much greater rate than what was predicted from the early data. So that Amori p-value is changing over time, so that these aftershocks are falling off more quickly over time than you would initially predict. And we believe that's probably because of pore pressures decreasing since the well has been shut down for the last 2.5 years. Okay, I'm going to finish up here. This is my last set of information for this talk. I just wanted to show you where those largest aftershock earthquakes have occurred recently. I told you the 3 of our 7 largest earthquakes had occurred, more than a year and a half after brine disposal was shut down, and that they were all in this new seismicity cluster. Prior to the occurrence of this earthquakes, we saw no deep earthquakes over here. All the earthquakes were very shallow. They appeared to be stress induced, but these deep earthquakes occurred since the well's been shut down. So I just have a few time lapse here. The first earthquake occurred just a couple weeks after the main shock, so it appeared to be an aftershock of that earthquake. We had a few more in April of that year, including a magnitude 2.5, but then we had very little occur for more than a year. So this is going through June 2020. We had almost nothing occur over there. And then July 2020, we started getting a little bit of expansion of that cluster. October, November, we had several more. December, we had 4 significant earthquakes over there. We had another one in January of 21. And after that, the seismicity rates really greatly declined. So this is through July 21. And just quickly to show you this in cross-sectional view, the cross-sections on the right are parallel to that main fault plane of the main shock. The cross-section on the left is perpendicular to that new seismicity cluster. And you can see it's a very planar feature, seem to be activating a single fault. So here's just a time lapse in cross-section view. You can see that earthquakes occurring up and down that fault over time. And again, even though these earthquakes started in the aftershock zone, the rates at which they occurred last fall just don't fit the Amori aftershock decay relations at all. If we include that western cluster, the blue dashed line shows how much the observed seismicity deviates from what you would expect for aftershock behavior. If you exclude the western cluster, then the aftershocks really match the predicted behavior. So although these are in an aftershock zone, they appear to be being triggered by something other than strictly stress redistribution from that fault plane rupture. And finally, we also just did a quick B-value analysis on that western cluster, and it has a anomalously low B-value of only about 0.4. So near-term activities, we're currently performing a probabilistic seismic hazard analysis that needs to be completed before a decision is made whether or not to resume injection into this well. A risk analysis is planned for next year, so that would be an engineering level risk analysis. We're currently completing some analysis related to the March 2019 earthquake and aftershocks and trying to prepare some publications to get out on that analysis. And we're looking at we have a coupled pore elastic geomechanical model that we have in-house that we're using to try to better understand this post-injection seismicity that we've been observing. And we're also preparing an updated release of the earthquake catalog and injection data. And I will just leave you here with the website in case you want more information about this project. There are a lot of reports available on this website. So I hope you'll visit that sometime. I have no idea what time it is. I hope I didn't run too long.
No, this is terrific. That's a really great talk, Lisa. Thank you. We do have some questions. It's always great to see the attendees tossing questions into the chat box. If you have any questions, please put them in there. So I'll just go right ahead and kind of read through the ones. I have a couple myself, but the attendees have some great questions. Peter Hennings here at UT Austin asked, have earthquake hypocenters been used to assist with fault interpretation, or were other data used exclusively?
Okay, so the faults that I showed you that are on the geologic maps, those faults are interpreted from seismic reflection data and well logs. We reprocessed a couple 100 miles of seismic reflection data and did a big geologic interpretation a few years ago. Those are not the faults in which the earthquakes are occurring. We have interpreted other smaller scale faults on which the earthquakes themselves are occurring. And we published a paper in Geophysical Journal International about that back in 2015, I believe. So we have interpreted other faults that I have not showed you because I couldn't include everything in this talk based on the earthquake hypocenters. They form some very linear patterns, and they very clearly show a conjugate set of faults that a lot of these earthquakes are occurring on. Right.
Okay. Thank you. Michelle Goucher asks, has there been any correlation made between on-off cycles of injection and events? Any water hammer effects possibly?
I'm not familiar with that term, water hammer effects, but I have not seen any indication that seismicity is caused, I assume you're meaning if seismicity is caused when the well is turned on and off.
Correct.
Yeah, and I haven't observed that. The seismicity used to respond pretty quickly to shutting the well on and off in terms of not immediately when it went on and off, but if you you injected, like during those early tests, you would inject for a couple months and then shut down, your seismicity would fall away after you shut down. That doesn't even happen anymore,
Right.
Not to a great extent because we've been injecting for so long, but I've never seen any evidence that the actual turning on and off of the well itself has caused earthquakes.
Okay, great. And just really quickly, what's your magnitude of completeness for your network? Because you had a lot of minus really, really small events you were able to see.
Yeah, well, that has varied enormously over time, as you can imagine, because this network's been operating since the 1980s.
Mm-hmm.
When we try to analyze the data as a whole data set, we generally say 0.5 or larger. But when that 2019 earthquake occurred, actually every one of our seismic stations was online and functioning perfectly. And it was in the winter when the noise levels were really low. So we actually went down to like minus 0.5 during that event. So it varies, but I think overall I would say about 0.5, but at times it gets down to as low as like negative 0.5.
Oh, that's great. Ryan Schultz asks for the stratification of the hypercenters with depth. How certain are you that this is a robustly observed trend? Is there the possibility that a refined velocity model may change that result? Just curious as to some of your thoughts, as this is a very interesting result.
No, I don't think the stratification, I'm assuming you're talking about the stratification of the aftershocks of the 2019 earthquake into those two distinct layers. I don't think that is an artifact of the velocity model. I mean, we saw that when we were using the regional scale velocity model that has very low spatial resolution in that area. And then we did that much higher resolution velocity model. And we still see the same, there were slight changes in maybe the dip of some of those layers, but you still see very strong stratification. So we've located it with two very different models and gotten very similar overall trends. So I think that's really pretty robust.
Oh, that's great. Yeah, it gives you a lot of confidence when you're looking at this from two different sets of data. John Webb asks, is the well-completed open hole from Mississippi and Leadville all the way to total depth in the Precambrian?
It is not open hole anywhere. It's perforated. I think they cased it all the way to the bottom, and then I don't know how exactly they perforated, but they put some perforations in. So there's some distinct perforated zones. There's, I think, 3 zones in the Leadville, and there's 2 or 3 zones deeper in some of the deeper sedimentary layers, and then I think 1 zone in the Precambrian, upper Precambrian. We had some early flow tests run early on, maybe during the injection tests or early during continuous injection, that showed that more than 80% of the flow was going into the uppermost Leadville perforations. And actually some other surveys of the well later on, I think in 2001, showed that the bottom of the well has been filled with elemental sulfur. So I think all those perforations are plugged, and the interpretation was that they got plugged because there was no flow, basically no flow going into them in the first place. So things precipitated out and plugged up those deeper ones.
Oh, great. That's very interesting. So a real quick question, the seismometers that you've installed in the network, what kind are they? I'm sure they're multi-component, but are they shallow burial? Are they borehole seismometers? Are they cased in rock? How do you, because that's a really, really clean signals that you're getting.
They're not cased in rock. I mean, the sites are sited on rock. So somebody went out and jackhammered into the rock and created these vaults. So the vaults themselves are set into bedrock. And the seismometers are GURLP. Oh gosh, don't remember the model number. My coworkers who are on this call might be able to chime in with the model numbers, but they're I don't know if they're borehole seismometers or just regular seismometers. Chris, are you on?
I am. So the seismometers are GURLP model 3 ESP CDE, so just a standard broadband fairly quiet seismometer, 3-component, and they're installed in these fairly quiet, dry vaults about a meter below the ground surface.
Yeah, and like I said earlier in my talk, all these sites are in very remote locations. So there's not a lot of cultural noise. The biggest noise we get on them is wind, if the trees are blowing around. But it's a quiet area because it's in the middle of nowhere.
Yeah, how lucky you don't have pump jacks running everywhere. Yu Chen Zhao asks, is it possible that the zigzag injection pattern prevents the pore pressure buildup far distance? Therefore, the pressure buildup is occurring near distance.
I don't think I understand the question. Maybe you could help explain this to me, the zigzag pattern.
Well, I think that so in terms of the buildup and the lessening of your downhole pore pressure in the way that you're doing your well shut in. That's my understanding. And Yu Chen, if you can unmute, you can ask the question.
Yes, that's exactly correct. So my question is, I think before 2015, the injection period is longer. So it's shutting is like maybe 2 weeks, but then afterwards you have like shutting periodically like in 2 or 3 weeks. So my question is, does that, because you don't have a longer time of continuous pumping, does that prevent the pore pressure buildup at far distance? Therefore, the zigzag injection pattern only increase the pressure at a shorter distance.
Now, I actually kind of think it's the reverse, because the pore, we've done this pore pressure modeling and looked at pore pressure trends at different distances from the well. And when you get more than 4 or 5 kilometers away from the well, it's pretty insensitive to what you're doing with shut-ins. So the pore pressures at the greater distances, they don't really react to your short-term shut-ins. It's the stuff that's close to the well that where the pore pressures respond to the length of your shut-ins. So the pore pressures beyond 4 or 5 kilometers, they're just continuously increasing, and they don't see these 20-day shut-ins.
Okay, thank you.
Great, thank you. And finally, so this will be our last question. This is from Rex Buchanan at the Kansas Geological Survey, and this is sort of a question I had as well. Okay, so you've this Class 5 well has been shut in. It's a really vital program for reducing salinity and downstream. What are you doing now? I mean, how is the salinity in saline water? What's your management of that brine?
We're not managing the brine. So this project has no storage for brine. So the injection well and the extraction wells are synchronized. So the extraction wells can only run if the injection well is running. So since the injection well has been shut down for the last 2.5 years, that means we're not extracting the shallow brine, and it is going into the Colorado River system. I saw some very interesting pictures a couple of months ago that one of our coworkers had that showed the river turning black in Paradox Valley from all the brine that was entering that river. But yeah, it's gradually increasing the salt load in the river right now. So we're working with these other, seismic analyses done, so our upper management can make a decision about whether or not to bring this well back online.
Right, just as the drought is reducing snowmelt.
Yeah, it all compounds itself.
Yep. Well, Lisa, this is terrific. What a great talk, and we appreciate you're getting lots of accolades. People putting accolades down on the chat box. I thought it was just great. And thanks everybody for being here. I just want to mention really quickly that our next webinar is going to be October 21st. It is going to be a panel, so it'll be a panel format like we've had in the past. And that panel will be led by Paul Aguari at the Oklahoma Geological Survey. And so we will give everybody a minute back of their day. The talk will be posted on our website at the Bureau, beg.utexas.edu/risk. And you can see the talk there. It'll take a couple days to post-process, then we will upload it, and it will be available also on our YouTube channel. Lisa, thank you very much again, and really terrific. And best of luck with the program going forward, and everybody be safe, and we'll see you in a couple of months.
Thank you.
Okay, thank you. Okay, we could turn recording off.
It was turned off.
Excellent. Okay, awesome.